So we'll now
Thank
move
you.
to our final presentation. Going to be given by Matt Glisson, who makes his second appearance here at the It's Money webinars, and he's going to talk about rebuilding the Red Wing recycling facility. Matt, the floor is yours.
Thanks, Gerald, and thank you very much for inviting me back for a second round. I guess that means I did well enough on the first one. Hopefully I can live up to expectations again and the quality that we've gotten so far from John and Joe. I'm going to talk today about what the work that we did rebuilding the Red Wing Recycling and Refuse Derived Fuel, or RDF facility. The project occurs at the building that was constructed in 1982, but in 2017, in June that year, there was a pretty significant fire, as you can see here in the picture. It wound up requiring over 70 firefighters to put the fire out. It damaged about 9,000 square feet of the 36,000 square foot facility. Fortunately, no loss of life or no significant injuries, but the building itself did have to be demolished. It was deemed unsafe for occupation or use again. So quick orientation for you all of the facility itself. In red here is the original 1982 portion of the project of the facility. In yellow, we have a addition that went in the 2008 time period. And then over here in orange, I've got highlighted a tannery that exists next to the City of Red Wing's property. And I'm pointing this out because it's going to come into play a little bit later on in our discussion. Just so happens for any of you that happen to be proud owners of Red Wing boots, you can be assured that your leather came through this tannery facility just south of downtown Rochester. So in February 2018, we received a request for proposal from RRT, the lead design consultant, and they wanted to reuse the existing structural slab and timber piles shown in the red dashed outline here on the inside, the white area, but they also wanted to add on to the existing structure or the original previous structure, improve their facility a little bit, and those are the gray shaded areas that you can see here. The request for proposal included performing additional borings, performing some environmental sampling and testing, and an evaluation of the existing timber piles. Included in that RFP was the geotechnical report that Braun Intertec actually performed for the FFC and MRF edition, which is the 2008 edition, and that's the front-end fuel cleaning and material recovery facility. So we had that information already, but it was good to get it again. And then the construction records were not provided to us, but we knew that we had those in our archives. We knew that the project went in on driven pipe piles, closed end, 12-inch pipe piles at that. They also provided in the RFP the geotechnical report prepared by another firm for the incinerator addition that went in 2017. Through the process of pulling together our proposal, we did figure out that yes, we did do or were part of the 1982 construction. Unfortunately, the construction records that the owner had were destroyed because they were housed in that 1982 facility. So we knew we were involved in it. We weren't sure if we did actually have project records and what we actually did have or not have. We knew that if we had them, they were in our offsite storage facility. Unfortunately, we weren't going to be able to get those from that facility in time to respond to the RFP in the deadline that they had asked for. And we also knew that we were part of a solar panel project that went in on drilled shafts. So a little bit going back to the aerial shot for you here. This is taken in early 2017. You can see that the 1982 portion has been demolished. And again, the 2008 edition in here. The solar panel array is just south of the 2008 edition, and then the incinerator building that went in a little bit further to the south. So we've got some pretty good geotechnical information surrounding the facility, and we felt comfortable putting together a decent proposal that did not include doing additional borings and environmental sampling. from the previous geotechnical work that we'd done out there. We'd encountered fur, we'd encountered hides. We knew that whatever was excavated from the site would have to be sent to a permitted facility for disposal. So we broke our proposal up into 3 phases: a desktop review, which would include geotechnical static evaluation of the timber piles as far as the resistance that they could have from the geotechnical side of things. And then say in the second phase, we were going to perform some ground penetrating radar to determine where on the inside of the existing building or the original building we could perform some test pits. Again, back to the structural slab that was there. We knew we needed to pick where we put the holes in that structural slab for performing some visual observations and hopefully some testing of the timber piles. The pile evaluations were going to include visual observation, sounding what we could expose with a hammer to evaluate the integrity of the exposed portion of the pile, and then performing sonic echo, impulse response, low strain integrity testing, multiple terms that are used for that, to evaluate both the integrity and the as installed length. And then the last part of it was the geotechnical evaluation portion, using the available information that we already had to develop recommendations for the addition, or if needed, additional foundations for the original structure. Pretty decent fee when all said and done. We've got 3 days out on site of work to do. I mentioned the sonic echo impulse response method of testing, and for those of you not familiar with that, it's based on one-dimensional stress wave theory. You're going to apply a stress wave at the top of the pile, and using a uniaxial accelerometer, you're going to measure what the response is. And you're going to get a reflected wave from a few different things. First off is a change in the material properties of the pile. Maybe that's a reduction in the cross-sectional area as shown at this little notch out here. It could be a strong soil resistance as shown by this R here and the reflected wave back up. Ideally though, hopefully if all things go well, you're going to see a response from the toe of the pile, and that's going to be the strongest response that you see after the impact pulse. And we can take this type of information, knowing that we are going to be impacting the top of the slab and not actually the top of the pile. We're going to have our accelerometer partway down the pile. We can estimate the wave speed for the stress wave traveling down that pile and use that to back our way into what the length of the pile actually is, and use that as well to evaluate the integrity of the pile. We have a theoretical known of what the pile is because we knew from the design drawings that were still around that they were supposed to be 60 feet long, or 50 feet long, excuse me. We didn't know what the actual lengths were yet at the time that we put the initial proposal together, because we were still trying to retrieve that information from our archives. Turns out we did have some pretty decent information about the existing piles. We actually had the records that showed the final lengths that they were installed to, the final penetration resistance, and the final stroke of the hammer that was driving them. So going from testing at 16 test pits with looking at 48 piles, which was 10% of the piles installed, so 470 piles were installed, taking that down to 5%. We felt comfortable doing that. We didn't need to test as many piles now that we have that additional source of data that can guide and help us evaluate what the piles actually have out in the field. Still comes in at a pretty decent fee. And at this point, I need to tell you all that this is a rebuild, right? A fire happened, so the owner isn't paying for all of this work. An insurance company is. And working with the insurance company wound up to be a very good thing in this case, because it forced us to justify the expenses that we wanted to have them incur, right? Insurance companies don't want to give out money if they don't have to. Understandably, most of us don't. So we had to walk through the exercise with them of, if we spend this much, here's the potential savings in construction that you're going to have, or in design costs that you're going to have. At the end of the day, they still thought that this $35,000 proposal was more than they were willing to spend. The $35,000 doesn't include fixing the structural slab, patching that back together, that they could actually reuse it. So through the conversations with them and the owner and RRT, we decided that, okay, we can reduce our scope further as long as we're not bearing the risk of identifying whether or not the piles are suitable from a structural integrity standpoint. So take it down to doing 2 test pits, looking at 4 to 8 piles. We're not going to provide a final conclusion with looking at that few piles of whether or not the overall number of piles is suitable for carrying the existing structural load or whatever new structural load they're going to have on it. We're still going to do the desktop review. We're still going to do the geotechnical evaluation, and we ended up at the $16,000 fee. Now, I'm guessing at this point, a few of you are wondering if I realize what this presentation is about, right? Increased testing saves money, but here I am talking about how we kept reducing our scope and our fees. It's still an increase in testing. Reason being, they could have done nothing. They had the historical geotechnical information. We could have taken that, spent $4,000 or $5,000 of a fee, and provided them recommendations for constructing a new building. They could have ignored the existing foundations. They could have ignored the existing structural slab, and they would have saved themselves $11,000, $12,000, and maybe not actually saved that on the construction side of things. They also could have gone through and done our phase 1 portion. So do phase 1, do phase 3, spend about $8,000, $9,000 based on the construction records that we were able to find that we had. Still would have been less than the fee here of $16,000, but still would have been lower amount of testing. So I'd say that increased testing saves money, but I'm going to add a little caveat, right? There's an exception to every rule, and that's to a point. And there does need to be a perspective that we look at. John did a great job and Joe did a great job of showing how increased testing really did save significantly large amounts of money going forward for those projects. In our case, that wasn't the situation. Spending another $18,000 or $30,000 wasn't going to save them as much money. So now to the conclusions of what we did with our evaluation and what we end up seeing. And I'll start off with the desktop review that we did. We looked at 3 different dynamic formulas, the FHWA modified gates, the Minnesota Department modified ENR, Department of Transportation, modified ENR formula, as well as their 2012 formula that was based on research that they did to develop resistance factors for the LRFD methodology. It did incorporate looking at static and dynamic load test data that they had in their files for timber piles, pipe piles, and H piles, although the number of timber piles was relatively small. So the conclusions of that, the authors did conclude that this formula probably is not representative and should not be used for timber piles. We thought it was worthwhile to include it, as it did have some timber piles in the database. We thought it was going to be a worthwhile comparison. We weren't sure if maybe going from ASD to LRFD would allow us to utilize some additional resistance or capacity that the piles might have had. Turns out that the designers didn't want to go that route. They wanted to stay with ASD, which is fine. We still went ahead and went through the exercise. It was one additional equation to formulate in Excel and then copy and paste it down for the 426 piles that we actually had sufficient information to run through a formula. So we were missing about 50 piles to do that evaluation from. It still showed overall that the allowable, the minimum allowable value that we calculated for all the different lengths and penetration resistances was coalescing right around that 70 to 80 kip range. The average was a little bit higher at 80 kips, except for the one value for the MPF 12 that came out at 108. So we started to get some coalescing and some general feel that, yeah, that 35 tons, 70 kips is about where we're going to be. Lastly, we performed a static analysis using Meyerhoff SPT methodology. We took an average pile length from the project. The range of pile lengths was 32 to 67, and then the average wound up being 44 feet. So that's the number that we took and plugged into our evaluation using Meyerhoff, and lo and behold, wound up right around that 70 kips allowable resistance value again. So stuck with that. Unfortunately for everybody involved, that 35 tons, that 70 kips, that was the original design. So we weren't able to show that they have any excess geotechnical resistance in these piles, but still needed to look at the structural side of things. What's the integrity of the piles? Due to site conditions, we were only able to evaluate on the east side and the north side due to the west side having concrete slabs that the owner really did not want to disturb for evaluation purposes. And obviously we had the 2008 addition on the south side. So start off with looking at the east side, general overview of where we were digging, and that was going to be in this area right here. You can see that it's down to the slab and the cast in place walls that were from the 1982 structure. And here's what we saw when we opened things up. Got down to the timber piles, and we're able to expose piles 51 and 52, right and left there. And zooming in, you can see that it's fairly well preserved. We also get lucky in that there is a decent void underneath the existing slab that allows us to look in and see some additional piles in addition to the two that we're right on the edge. So that gave us the ability to look at a few more piles, not necessarily test them all out, but to at least look at them. And then this picture shows you the pulse echo instrumentation. We've got the accelerometer here attached to an aluminum block. One of the things with pulse echo is that you've got to have your sensor aligned axially with the stress wave. So we couldn't just attach the sensor to the side of the pile in that perpendicular direction. We wouldn't get the good response. So we've got it attached to the aluminum block, which is then bolted to the timber pile itself. Looking at the north side, we've got asphalt pavement in this case. They were fine with us tearing that all out. They, had some distress anyway. They were probably going to replace it with part of this project. And looking in a little bit closer, this area had a little bit more of a void. So we're actually able to see and evaluate and actually look at and sound with a mallet 3 piles. We didn't end up actually performing any pulse echo testing at this location due to inclement weather moving in the afternoon. We had 1 day for everybody to be on site, the contractor, representatives from the owner and the lead designer, and it just didn't work out that we could get back out there. They didn't want to leave it open and having water getting in here if they didn't have to, so from rainwater. So we covered everything back up. Unfortunately, weren't able to do additional pulse echo testing, like I said, but we did get the chance to look at more piles and verify the pile layout and spacing was per the plans. Looking at our impulse response results, calculated wave speeds were pretty close together. Apologize, that's supposed to be a comma. I'm not switching to metric in this unit here, or in this result here. And the calculated lengths that we came up with were within 3/4 of a foot of the reported lengths per the records that we had, which is well within reasonable expectations for sonic echo impulse response testing. Example of the data, here's the wave passing by the accelerometer with the impact and the pulse coming back up from the toe. To the last phase of the project for us, providing recommendations for them going forward. A little bit of the profile out here, and this leads to why there was the void underneath the slab. And it's that we've got fill that have been placed up to 24 feet thick, over 5 to 15 feet of organic deposits. And then we've got loose to medium dense sands, increasing strength with depth over glacial deposits. And we had groundwater relatively shallow, not high enough to fully preserve the timber piles, but apparently with the preservative that they had, it was still good. They were still fairly well maintained. So what do we think of for possible solutions? We looked at everything. We really weren't sure what the best solution was going to be when we started out with this project. We knew obviously that we had the environmental conditions. Anything that came out of the ground was going to have to go to a permitted facility. So if we could stay away from drilled shafts, RCAS piles, sorry, John, or micropiles, that would be a good thing. Push piers, driven piles, helical piles, those were all on the table. We knew there was going to be some uplift loads, so push piers start to get maybe a little less favorable. And then we started looking at the loads that they were going to have. We're going to have 100 kip column loads. Unfortunately, those columns were going to be located in areas that were not going to have a structural slab. So those were going to be isolated columns. They didn't want to use grade beams connecting them together to maybe get away with using one pile element that wasn't 24 inches in diameter, or having a couple of piles braced to meet IBC requirements. So we're looking at having 3 piles underneath these columns. That brings the loads down to 33, 34 kips, relatively low loads from a deep foundation perspective. We've got organic soils that we need to consider as far as the long-term durability, corrosion aspects. Ultimately, we were down to micropiles that would do favorably getting through the debris that was in the fill. They'd be grouted, they would have corrosion protection. However, they were going to have to go to significant depths in order to get the resistance that they were going to need, versus a grouted helical pile, going to have a little bit more trouble getting through the debris, going to have some piles that probably refuse shallow. And we are also aware of multiple cases where helical piles, quote unquote, run in water-bearing medium dense sands. So we recommended that they perform a static load test to develop a site-specific torque correlation factor, which they did. And they used grouted piles to control corrosion through the organic zones and the fill zones. And it wound up being the lowest cost alternative. Now, that didn't mean that there was not a change order submitted by the contractor for additional funds after the helical piles were installed. And it wasn't because they installed additional length of helical piles from their base bid. They actually installed 600 feet shorter. However, it took them an additional, 14 working days to install the piles because of the trouble that they had with encountering shallow refusal on debris, having to offset, move things over, and install some additional piles. Going back and forth with the owner and the contractor, it was decided that they were justified in that additional cost. Their initial time estimate matched up well with what we thought it was going to take, and we told the design team what it was going to take for installation schedule, so they rewarded the additional cost. We did talk with that contractor further after this project was done, and they had looked at the micropile costs as well, and even with the change order, the helical piles did come in at a lower cost than what the micropiles probably would have cost. So takeaways for me for today, working with insurance companies can be a good thing. It does force you to go through the additional, taking that exercise of what's the cost and benefit, taking that all the way to completion. Increased testing does save money to a point, right? Take a look at what the value you're going to add to the project by doing that increased testing. There might be a point at which if we do this one little increment further, we're really not gaining any additional benefit. And then for me, a lot of times I hear geotechnical engineers and other engineers talk about doing additional testing in the construction phase, right? We do another static load test. We do additional integrity testing during construction. And that's where we're going to get the biggest bang for the buck, right? It allows us to use that lower safety factor that John was talking about in his presentation. But as John showed, and as this presentation shows, sometimes doing additional testing during the design portion of the project can also be a significant savings for the project. And with that, I should acknowledge the help that we got for this presentation and this project, obviously from the City of Red Wing, the lead designer RRT, and the contractor that installed the helical piles and gave us some pricing information on the micropiles afterwards in Bolander. And with that, I will toss it back to Gerald and